Welcome to the second part of Euclidean Geometry. In this part, we are going to look at grade 12 Euclidean Geometry. This is only for grade 12. We will start with the proportion theorem and then look at two conditions for similar triangles. And finally, we will look at the Theorem of Pythagoras and then solve some problems based on the proportion theorem and the similarity as well as the Theorem of Pythagoras. So let's start with the proportion theorem. The proportion theorem says a line drawn parallel to one side of a triangle divides the other two sides of the triangle in the same proportion. Here we are given the triangle ABC with the line DE drawn parallel to the third side BC. This theorem tells us that DE divides the other two sides, which is AB and AC, in the same proportion. That means the ratio that we make with the side AB will be equal to the corresponding ratio that we make with the side AC. Let's have a look at the ratios that we have here. If I make the ratio AD over DB with the side AB, that will be equal to the corresponding ratio AE over EC with the side EC. Similarly, if I make the ratio AD over AB with the side AB, that will be equal to AE over AC. We can also do the same with AB over BD and AC over CE, as long as the side DE is parallel to the side BC. This is the reason that we use for this theorem. So you can simply write the whole statement proportion theorem or prop theorem. Remember, when you are working with Euclidean geometry, you always need to provide a reason to show which theorem you are using or you have used to arrive at that particular statement. Let's now look at the converse of this theorem. The converse of this theorem says, if a line divides two sides of a triangle in the same proportion, then the line is parallel to the third side. So this is the important part. What the theorem says is, if we are able to write the ratio of the side AB, and we find that that ratio equals to its corresponding ratio with the side AC, then we can conclude that the side DE is parallel to BC. That is the most important part. And this will be the reason that we use for that to be the converse of the proportion theorem. So if you find that you've been given the sides of the triangle, and then when you express the sides of that triangle, they give you equal ratios. Let's say you write the ratio of this side, and you find that it is equal to the ratio of the other side, the corresponding ratio of the other side. Then you can conclude that DE is parallel to BC, and you would write that as the reason for that statement. So DE would be parallel to BC. The special case of this theorem is the midpoint theorem. The midpoint theorem was covered in grade 10. The midpoint theorem says the line joining the midpoints of two sides of a triangle is parallel to the third side and equal to half the length of the third side. In this case, we are given the triangle ADE with BC drawn to the midpoint of AD and the midpoint of AE. What the theorem says is that this line, which goes to the midpoint of AD and the midpoint of AE, is parallel to the third side DE. Therefore, BC in this case will be parallel to DE. BC will be parallel to DE, and also that line BC will be half the length of DE. In other words, if DE is 20 units, BC will be 10 units. And the reason that we use for this, you simply write midpoint theorem. This is the midpoint theorem. So you just write midpoint theorem to show which theorem you are using to arrive at that statement. So we can show that BC is parallel to DE. The midpoint theorem also has the converse. The converse of the midpoint theorem says the line drawn from the midpoint of one side of a triangle parallel to another side bisects the third side of the triangle. Remember, in the midpoint theorem, this line BC was the midpoint of AD and AE. But in this case, we are told that it is parallel to the third side and it is a midpoint of one side. Now, what this converse says is that if you find that there is a line that is parallel to the third side and it is a midpoint of one side of the triangle, then it is also the midpoint of the other side of the triangle. In our situation, the line BC is a midpoint of the side AD and it is parallel to BC. BC is parallel to DE. Therefore, it is then also the midpoint of AE. In other words, AC will be equals to CE. So if you are solving a Euclidean geometry problem, you come across a triangle in which the two sides are parallel to each other, and this line is a midpoint of one side of that triangle, then you know that it will also be the midpoint of the other side of the triangle. And this is the reason that you use is the converse of the midpoint theorem. Let's now look at a quick problem that covers the proportion theorem. We are given two triangles here, the triangle ADE and the triangle ABC. In this case, we are given that BC is parallel to DE, shown by these arrows. And here we are given that DE is parallel to BC, shown by these arrows. And this is the information that we are given on this triangle. We are also told that the side AD, now this side AD is for this triangle ADE. So the side AD is 10 units in this triangle. We are required to calculate the values of x and y. X in this triangle, y on the other triangle. Now we see that BC is parallel to DE in this triangle. That means we can actually express the sides of this triangle as equal ratios. We could say AD, because we have the whole side AD, we could say AD over DB equals to AE over EC. And we would give the reason proportion theorem. We need to show, you always need to show which theorem you are using to arrive at this statement. We know it is the proportion theorem because DE is parallel to BC, shown by these arrows. Then now all we have to do is to substitute the values. Remember, AE is the whole side, so it will be x plus 3. And then now we can simplify this to find the value of x, in which case x is 12 units. In the second problem, the triangle ABC, we are given all the three sides except the one that we are looking for. We are given AD, DB, we are given AE, and we are looking for Y, which is EC. We can express this as AD over DB. AD over DB, we have all these sides, and then also AE over EC. Remember to always put the reason. The reason is the proportion theorem. Now we can simply substitute to arrive at the value of Y, where Y is 18 units. Let us look at another example. In this example, we look at the problem that requires us to use the knowledge of the midpoint theorem. We are given that N is the midpoint of AX, that Y is the midpoint of AB, and that M is the midpoint of BX. The first problem wants us to prove that YBMN is a parallelogram. The second one wants us to prove that MR is half of BC. Let's start with the first one. To prove that something is a parallelogram, we need to show that the opposite sides are parallel to each other. Remember, parallelogram is any four-sided figure whose opposite sides are parallel to each other. So in our situation here, if we can show that yn is parallel to bm, and then also show that mn is parallel to by, then we would have shown that ybmn is a parallelogram. Let's look in this triangle XAB or XBA, this triangle here. If you look at the line MN goes to the midpoint of AX and BX. Remember the midpoint theorem that we dealt with? If a line is drawn to the midpoint of the two sides of a triangle, then that line is parallel to the third side. In this case, MN will be parallel to AB. But if MN is parallel to AB, it should also be parallel to BY, because BY lies on the same straight line as AB. So we can show that MN is parallel to YB because of the midpoint theorem. If we look in triangle ABX, MN goes to the midpoint of AB, it also goes to the midpoint of AX. Therefore, YN will be parallel to BM because of the midpoint theorem. We have shown then that the opposite sides of this quadrilateral are parallel to each other. We have shown BM to be parallel to YN and MN parallel to YB. Therefore, YBMN is a parallelogram because its opposite sides are parallel to each other. Now we are required to show that MR is half BC. There are different ways you could do this. The approach that I am going to use here will start with this side here. Let's look at this triangle XAC. Triangle XAC or XCA. We are given that NR is parallel to AC and also NR goes to the midpoint of AX. Remember the converse of the midpoint theorem. If a line is drawn parallel to the third side and it goes to the midpoint of one side of the triangle, then it is also a midpoint of the other side. So in this case, NR will also be the midpoint of XC, which means XR will be equals to RC. And the reason will be the converse of the midpoint theorem. I can write BC in terms of BM or MB, MX, XR, and RC in terms of these smaller sides that make up BC. So I can say BC is MB, MX plus XR plus RC. But these two are equal to each other from what we're given here, right? We know that MB or BM equals to MX. It's given on the structure. This is given to us. Also, XR equals to RC. We've just proven it here because of the converse midpoint theorem. That means I can write this as 2mx and write this as 2xr because MB and MX are equal, XR and RC are equal. So if I take out 2 as a common factor, in brackets I have MX plus XR. Remember, I am trying to show that MR is half BC. So at the end of the day, I should have MR. But if you look at MX plus XR, MX, XR, this gives us the length of MR. The 2 give us MR, so we can simply write that as 2MR. If we divide both sides by 2, therefore MR will be half BC. Let us look at the last example on the proportion theorem. In this example, we are given that BF equals to 25 meters. We are also given that AB equals to 13 meters, AD equals to 9 meters, DF equals to 18 meters. And we are required to calculate the length of BC, CF, CD, CE, and EF, and also to find the ratio DE over AC. Let's start with the length of BC. BC, let's look at the triangle FAB. In triangle FAB, we are given AB is parallel to DC. Remember the proportion theorem? If you are given a triangle and then these two sides are parallel to each other, you can express the sides of that triangle as equal ratios. So in this case, we can express FA over AD. Remember, we're looking for the length of BC. So we can say FA over AD because we have the whole of FA, which will be the sum of 18 plus 9. And then we also have AD. In this side, the side FB, we have the length FB given to us here as BF. Doesn't matter whether it's a BF or FB, it's the same length, same distance. So FB is given to us as 25. Now the only missing part will be the BC. So now we can write the ratio FA over AD equals to FB over BC. And then the reason that we give is the proportion theorem because AB is parallel to DC. Then we simply substitute the right values. FA, remember FA is the whole length that adds 18 plus 9, so that will be 27 over AD, which is 9. FB is given to us 25, and if we can simplify this to get the value of BC, which will be 8.33 meters. Now let us find the length of CF, CF or FC. We still look in the same triangle, the triangle FAB, in which DC is parallel to AB. We can write the ratio FC over BC, FC over BC equals to FD over AD. We already have all this. We calculated the length of BC, so the only missing value will be the length of FC or CF. So if we write that ratio, the reason will be the proportion theorem because AB is parallel to DC. So we write FC over BC, FD over AD, and the only missing value here will be FC, which is what we are looking for. So if you do the substitution, we find that FC is 16.67 meters. And now let's find the length of CD. If you look at CD, CD is the side that is parallel to AB. And with the proportion theorem that we have worked on, we didn't have a ratio that involves these two. We are going to look at similar triangles. With similar triangles, we'll be able to express the sides, all the sides of the triangle, or as equal ratios. Now, these two triangles, if you look at the triangle FAB and triangle FDC, these two triangles will be similar to each other, and we will discuss this in the next section. They are similar to each other because they are equiangular. This line is parallel to that. This is parallel to AB. Therefore, this angle here will be equal to that angle. This will be corresponding angles. This angle here will be equal to that angle, corresponding angles. F will be common in both triangles. Remember, we are dealing with triangle FAB and triangle FDC. So in this triangle, this one equals to that one in that bigger triangle. And this angle C in this triangle FDC will be equals to this B here in the bigger triangle, and F is common in both. So these two triangles are similar to each other because they are equiangular. We can therefore express their signs based on the way we have arranged the equal angles here. So we can write CD over AB and write FD over AF. FD over AF based on how the angles are arranged there. We will talk about that in the next section. So after that, you can simply substitute the values and we'll find that the value of the length of CD is 8.67 meters. Let's now look at the length of CE. The length of CE, we have to look in the triangle FAC. In triangle FAC, AC is parallel to DE. In triangle FAC, AC is parallel to DE. Remember the proportion theorem? If in a triangle, this line is parallel to this line, you can write this side as a ratio that is equals to the ratio of this side. That means we can write FA over AD, FA over AD equals to FC over CE. You must see what we are trying to do here. We try to use the sides. So in the ratio, we try to use the sides that have length. So you don't want to write a ratio in which you have two unknowns because you wouldn't be able to solve that. So you make sure that however you arrange the ratios, you only have one unknown. So in this case, when we say FA, the whole of FA, we have 18 and 9, that's 27, so it's fine. AD is given to us is 9. FC, we've just calculated FC, 16.67 meters. So the only missing one will be CE. In this case, the length of CE. So it will be easier to substitute the values to find the length of CE, which is 5.56 meters. Let's now look at EF. EF, we still look in the triangle FAC because AC is parallel to DE. To find the length of EF, we can simply say AD over DF equals to CE over EF because we have calculated the length of CE, we have the length of DF, we have the length of AD, they are given to us. So the only missing length will be the length of EF. So if you substitute the values, you find that EF is given by 11.11 meters. And finally, to find the ratio DE over AC, we are going to use the same approach that we followed here of similar triangles. So if you look at the triangle FAC and triangle FDE, these two triangles will be similar using the same reasoning here because DE is parallel to AC. That angle over there will be equals to that angle. This angle will be equals to this, and the F will be common. Therefore, the two triangles will be similar to each other because they are equiangular. At the end of the day, you have triangle FAC similar to triangle FDE because they are equiangular. Then we can now express their sides as ratios. We can write DE over AC equals to DF over AF. Now I have chosen this because I have DF, which is 18 units, and I also have AF, the whole of this AF, because 18 plus 9, I have values for this. So I'll be able to find the value of the ratio DE over AC because I have the values for this. I have the length for DF, I have the length for AF. This can therefore be written as 18 over 27. Your DF is 18 is given, 27 is the whole length. And we can simplify that to 2 over 3. Let us now look at the similarity of triangles. Remember that triangles are similar if they are the same shape but differ in sizes. In other words, one of the two triangles will be an enlargement of the other. And also their position or orientation may differ. So if you remember congruent triangles that we dealt with in the previous grades, you remember that congruent triangles are the same shape, they are also the same size. So congruent triangles in this regard will be similar as well. So the first condition that we're going to look at is that of equiangular triangles. So equiangular triangles are similar. This is what the statement is saying. And this is the reason that we are using angle, angle, angle. So it shows that equiangular triangles will be similar to each other. Now we have this example here with two triangles, triangle ABC and triangle ADE, where D is parallel to BC. If you look at the two triangles, they have the same shape, they only differ in sizes. And ADE, triangle ADE, is also facing upside down, but it is the same shape as triangle ABC. So if we can now show that the matching angles of these two triangles are equal in size, we would have shown that the two triangles are similar to each other. So let's look in these two triangles, triangle ABC and triangle ADE. If you look at angle A1 and angle A2 are equal in size because they are vertically opposite angles. And if you look at these two triangles, you will see that these are the two matching angles of the two triangles. If we turn a triangle ADE up, this side would be the one that matches with this side of triangle ABC. So these two angles are so equal because they are vertically opposite angles. We are given from these arrows that DE is parallel to BC. So in that case, the angle B will be equal to the angle D. Those will be alternate angles because BC is parallel to DE. So B will be equal to D, alternate angles. In the same manner, C will be equal to E. Those will be alternate angles. The matching angles of these two triangles are equal in size. A equals to A, B equals to D, C equals to E. Therefore, the two triangles are similar. This is how we write it. We write triangle ABC is similar. This is the sign for similarity. 3 strokes facing up, 3 vertical strokes show that the two triangles are similar to each other. So triangle ABC is similar to triangle ADE. And the reason for their similarity is that they are equiangular. We simply write A to show that the two triangles are similar to each other. Now, because of this similarity, we can also express these sides as equal ratios. So we can actually write AB over AD, AC over AE, and BC over DE. These are the ratios that we can express. So let's say we are given triangle ABC, where DE is parallel to the third side BC. We are given D1, D2, E1, E2. So if we compare triangle ABC and triangle ADE like we did in the previous example, A is common in both triangles. Both triangles ABC and ADE, they share the angle A. So A is common in both. B equals to D1. Those are corresponding angles because BC is parallel to DE. In the same manner, C will be equals to E1. They are corresponding angles. And if you look at the two triangles that we're dealing with, ADE, ABC, A matches with A and it's common, we have it there. D1 matches with B, E1 matches with C. So the matching angles of these two triangles are equal in size, meaning that the two triangles are similar to each other. And the reason is angle, 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 or equiangular triangles. So this is to show that equiangular triangles are similar. So we can also express the sides as equal ratios. Let's put this in action. In this example, we are given that NKLM is a parallelogram with T on KL. Remember what a parallelogram is. A parallelogram is any four-sided shape whose opposite sides are parallel to each other. So in this problem, we know, since NKLM is a parallelogram, we know then that NK is parallel to ML and KL is parallel to NM, because NKM LM is a parallelogram. So we know the opposite sides are parallel to each other. Now the first problem wants us to prove that TXK is similar to NXM. So if you look at the two triangles, they are the same shape even though they are not the same size. Now we are required to prove that the two triangles are similar. To prove that the two triangles are similar, if we can show that the matching angles are equal in size, then we would have proven that these two triangles are similar to each other. Let's follow the order in which the two triangles have been written. So let's start with T and see if we can match it with N. So T1 equals to N2. These are alternating angles. This line is parallel to this line. Therefore, N2 will be equals to T1. These are alternate angles because KL is parallel to NM. Why is KL parallel to NM? We are told that this is a parallelogram, and we know that a parallelogram is a four-sided figure with the opposite sides parallel to each other. Let's look at the second part. X must be equals to X. So in this triangle TXK and XT, we can see that X2 will be equals to X4. These are vertically opposite angles. So X2 will be equals to X4. They are vertically opposite angles. Now let's look at K and M. K and M. In this triangle TXK, K2 will be equals to M1 in triangle NXM. So K2 will be equals to M1. These are alternating angles. Remember, KL is parallel to NM. So K2 equals to M1. Those are alternating angles. So now we have shown that the corresponding angles or the matching angles of these two triangles are equal in size. Therefore, we can conclude that triangle TXK is similar to triangle NXM. And the reason, angle, angle, angle. The second problem says we must prove that VXM is similar to NXK. So let's follow the same approach that we followed here. Remember that the line MV will be parallel to the line NK. We know that ML is parallel to NK, but MV lies on the same straight line. It's the same straight line as ML. Therefore, it should be parallel to this one as well. So MV will be parallel to NK. The angle V will be equal to N1. Remember, we are matching two triangles, the triangle NXK. So in this triangle, we are interested in this triangle and this triangle. So here we can show that V equals to N1. Those are alternating angles because NK is parallel to MV. X3 will be equals to X1. These are vertically opposite angles. X1 will be equals to X3 or X3 will be equals to X1. These are vertically opposite angles. M2 will be equals to K1. So M2 will be equals to K1. Those are alternating angles. Yes, because NK is parallel to MV. Therefore, the two triangles will be similar to each other. Triangle VXM will be similar to triangle NXK. The reason, angle, angle, angle. In this example, we are given that TS is produced to V so that the side SV is 2 times the side TS. We are also given that UV is parallel to PS, shown by these arrows here. We are required to prove that the triangle TQV is similar to the triangle PSV. If you look at the shape PQV, as V. This is a cyclic quad. It is the fourth theorem, the angles in the same segment. If you look, we have this butterfly shape with all its vertices touching the circumference of the circle. Therefore, P will be equals to T, angles in the same segment. S will be equals to Q, angles in the same segment. Therefore, we can show that the angle VPS, which is P, will be equal to the angle QTV, which is the angle T. These are angles in the same segment. So we have shown that this angle equals to that angle in these two triangles. Remember, we are trying to prove that this triangle TQV is similar to this triangle PSV. So we have shown that this angle in triangle TQV is equal to that angle in triangle PSV. So P equals to 3. T equals to P. V1 is common in both triangles. If you look, we have PSV, TQV. Therefore, V1 will be common in both triangles. So V equals to V. V1 is common in both triangles. So the third angle, we don't need to prove it. We could prove that since these two angles are equal to each other, and therefore, if we say 180 minus this angle would get the same angle here, 180 minus will get the same angle here. So these two angles will be equal, but we don't need to prove that. Once we are able to show that two corresponding angles are equal in two triangles, then the third one we can simply say is the third angle of a triangle, and this is an allowed answer that you can give. There's no need to prove the third one because they will automatically be equal as long as you manage to prove that two corresponding angles are equal to each other. So in this case, we have shown that the corresponding angles or the matching angles of the two triangles are equal in sizes. Therefore, we can conclude that the triangle TQV is similar to the triangle PSV, and the reason is that they are equiangular. We simply write angle, angle, angle. The second question wants us to show that QV times PV equals to 6TS squared. We can use these similar triangles and write the ratios, the corresponding ratios. The first one that I come up with is TV over PV because this will involve PV. So TV over PV, and then QV over SV. So I chose these signs because they have the PV that they want. They also have the QV that they're looking for. So if I cross multiply these two, I will have QV times PV, which is what they are looking for here. And it will be equals to TV times SV. Now let's revisit what we have already been given. We were told that the side SV is 2 times the side TS. That means TV, the whole TV, will be equals to 3 TS. See, I have 1 TS, I have 2 TS. So I have 3 TS's from T to V. So therefore, TV will be 3 TS. SV has already been given to us as 2 TS. So we can write this as QV times PV equals to 3 TS for TV times 2 TS. If you multiply 2 and 3, will give you 6. And TS times TS will be TS squared. Now let's look at the last condition of similarity. This condition says if the corresponding sides of two triangles are in proportion, then the two triangles are similar. And it's important that you test all the 3 corresponding sides of the two triangles. If you write the ratio of the corresponding sides and the ratios are the same, then the two triangles will be similar. And this is the reason that we use side, side, side. Let's try this condition using this example. In the diagram, we are given two triangles, triangle ABC and triangle ZYX. And we are asked if these two triangles are similar or not. So the question says, is triangle ABC similar to triangle ZYX? Show calculations. To prove that the two triangles are similar to each other, we need to express the corresponding sides as ratios. If the ratios are the same or equal, then the two triangles will be similar to each other. Now, by corresponding sides, I mean if I take AB over ZY, AC over ZX, BC over YX, all these sides or these ratios must give me the same answer. There must be the same ratio. Let's start with the first one and see. When we express the ratio of the side AB in triangle ABC over ZY in the triangle ZYX, we get 15 over 5, which simplifies to 3 over 1. If now we take AC over ZX, that gives us 18 over 6, which simplifies to 3 over 1. If we take BC over YX, that gives us 24 over 8, which simplifies to 3 over 1. Now, if you look at all the corresponding sides, when we make ratios of all the corresponding sides of the two triangles, they all give us the same ratio, which is 3 over 1. Therefore, we can conclude that the two triangles are similar to each other. And the reason is side, side, side. And finally, we get to the most popular theorem in mathematics, the Theorem of Pythagoras. And one of the cleanest way of proving this theorem is by using the similarity of triangles or similar triangles. It's one of the easiest and the cleanest way of showing that the square of the hypotenuse in a right angle triangle is equal to the sum of the squares on the other two sides. But I am not going to prove the theorem here. So what I want to show you is which triangles will be similar if you come across a problem that has the theorem of Pythagoras in this nature. So what is important is just being able to know which triangles will be similar without having to prove them first. So this is what I am going to show you. Let's say you come across a problem and you're solving Euclidean geometry problems, and then you come across a problem in which you are given a right-angled triangle, say ABC, where A is 90 degrees and AD is perpendicular to BC. Now, this extra condition is important for you to use this similar triangle. A must be 90 degrees and this must also be 90 degrees. So in that case, your triangle ABD will be similar to your triangle CBA, the whole triangle CBA, and then it will be similar to triangle CAD. So we have three triangles that are similar to each other here. Let's repeat this. It's triangle ABD, this triangle here. It will be similar to the bigger triangle, but we start from here, CBA, which will be similar to the triangle CAD. So the best way to remember this in a problem is to start at the outer 90 degrees. So we start at the outer 90 degrees of triangle ABC. We start with, so you start at A, you go anti-clockwise, B, D. So you start at the 90 degrees anti-clockwise, A, B, D. Then now you go to the other end. Start with C. Remember we said A, B, D. So now you start with C and take the whole triangle going in a clockwise direction. So it will be C, B, A. You go back to C again and then go in an anti-clockwise direction for a smaller triangle CAD. Let's recap this. You start at 90 degrees, go anti-clockwise A, B, D. You start at the other end C, you take the whole triangle C, B, A. You start at C again, and then now you take the smaller triangle, it's C, A, D. So those are the three triangles that will be similar to each other in this sort of a problem. And the reason that we use is Pythagoras or right-angled triangle. Let's do an example on this theorem. In example 6, we are given triangle XYZ. We are told that Y is 90 degrees, XYZ is 90 degrees, XYZ. And then we are also told that YT is parallel to XZ. So the two conditions of the theorem of Pythagoras are here. We have a 90 degrees and YT is perpendicular to XZ. This is the only thing that you need in order to be able to write those similar triangles. But we have also been given extra information that XY is 14 centimeters, XT is 4 centimeters. And they want us to determine the length of XZ and the length of YZ. If you look in this smaller triangle XYT, we already have the two sides. We have the hypotenuse and the other side. So we can use the theorem of Pythagoras as we know it and then find the missing side YT in that smaller triangle. So we can start there because we have all the information. So we use the theorem of Pythagoras to find the side YT. And when you simplify that, YT gives you 6 the square root of 5 centimeters. So now that we could do simply by using the theorem of Pythagoras as we know it. But if you look at this triangle, the XZ that they want, if you wanted to use the theorem of Pythagoras as you know it, by saying the square of the hypotenuse equals to the square of the other two sides, it wouldn't work because we don't have enough information here. If you say this would be our hypotenuse, XZ would be our hypotenuse. So if we take this hypotenuse, we don't have the side TZ, so we also don't have the side YZ. So there will be two unknowns here. We wouldn't be able to find that solution. So this is where those similar triangles come into play. So it's important for you to know which triangles are similar to each other in this kind of setting. Remember, the two conditions are already there. We have a 90 degrees and YT is perpendicular to XZ. Which triangles are similar now? Remember, we start at the outer one and then we at the outer 90 degrees and then we go in an anti-clockwise direction. So it would be YZT. YZT will be similar to the other end. We take X, Z, Y for the whole triangle. And then we start at X again, X, Y, T. So those are the triangles that will be similar to each other. It's YZT, XZY, XYT. So we have these three triangles that are similar to each other. This is very important. This is what you need to remember in this theorem of Pythagoras. So whatever you do, if you can remember how to find or how to show which triangles are similar in this situation, then you'll be able to solve most of the problems without having to actually start by proving the similarity of these triangles. So there will be three triangles that are similar to each other. You just need to know how to find those. So now we can answer this question, XZ, by simply picking any two triangles that are similar here, that have enough information that we can work with. So if you look at these two triangles, they can give us what we want. Remember, we are looking for the length of XZ. So if we say XZ over XY, remember we have XY, we can say XY, the whole of XY over XT. We have all these other three sides except the XZ that we are looking for. simply because these two triangles are similar to each other. We can substitute the values, and then our xz will be 49. To find the value of yz, let's look at the triangle that has the yz. This is our triangle. We can use these two triangles now to find the length of yz. So we can say yz over xz. We already have xz, we calculated it here. And then yt, which we have over xy, which we have been given. So all we have to do is substitute and then simplify, where we get our yz to be 46.96. That pretty much covers it, right? To the end of all that we needed to know before we start tackling exam type problems. So now we start with the type of questions that we will meet in exams. The first problem, we are given that A, B, C, D is a rectangle. We are also given that AB is parallel to GH. The first question that we are asked is to explain why FC is parallel to GH. And the second question, we are asked to calculate, also giving reasons, the length of DM. So you should be, by this time, you should be familiar with the properties of a rectangle. But let's revisit those properties for the benefit of this problem. A rectangle is any four-sided figure or shape whose opposite sides are equal and parallel to each other. So AB will be equal to DC and will be parallel to each other. BC will be equal to AD and they will be parallel to each other. The diagonals of a rectangle are equal in size or equal in length. That means AC will be equal to DB. They are the diagonals of a rectangle. They are equal in length. And also, the diagonals of a rectangle bisect each other. So that means AM equals to MC, DM equals to MB. So M is the midpoint of AC, and it is also the midpoint of DB. So those in passing are some of the properties of the rectangle. Now, with these properties given to us, they want us to explain why FC is parallel to GH. We know that the opposite sides of a rectangle are equal and parallel. That means AB is parallel to DC. If AB is parallel to DC, it should also be parallel to FC. So AB is parallel to FC because this is the same straight line. Therefore, AB is parallel to FC. It is parallel to GH because these are the opposite sides of a rectangle. These two are the opposite sides of a rectangle. Therefore, this line will be parallel to that line. Now, they want us to calculate the length of DM. Let's start with triangle AGH. In triangle AGH, we know from what we've just proven here or shown that FC is parallel to GH. We can use the proportion theorem to express the sides of triangle AGH as equal ratios. Remember, if you have FC parallel to GH in triangle AGH, you can express the sides of this triangle as equal ratios. So we can write AF over FC equals to AC over CH. That is the proportion theorem because FC is parallel to GH. But why are we doing this? We are doing this because we want to find the length of AC. We know that once we find the length of AC, the length of AC will help us to find the length of DM, the DM that they are looking for here. So we use this ratio in order to find the length of AC. And if you look in triangle AGH, if we use the proportion theorem, we have AF is given to us as 20. We have FG is given to us as 15. We don't have AC, but we do have CH. So we have all the other three except the AC, and it is AC that we're looking for. So we can substitute and find the length of AC as 28 units. Now we know that AC will be equals to DB. These are the diagonals of a rectangle. We know that the diagonals of a rectangle are equal in size. So we can simply put the reason as diagonals of a rectangle. And again, we know that DM equals to MB. The diagonals of a rectangle bisect each other. So therefore, DM will be equals to MB. Since DB is 28 units, that means DM will be 28 divided by 2, or half times 28, because the diagonals of a rectangle bisect each other. Therefore, DM will be 14. In the second problem, we are given a quadrilateral CDEF, and we are given these sides over here, which are also shown on these triangles. The first question wants us to show that angle EFD equals to angle ECD. So we want to show that this C here equals to that F over there. And the second one also wants us to show that angle DFC, this angle here, equals to angle DEC, that angle over there. And remember the second condition of similarity that we looked at. We said if the corresponding sides of two triangles are in proportion, then the two triangles are similar. We want to use this understanding here, right? We know that if we can show that these two triangles, triangle TFE is similar to triangle TCD, if we can show that these two triangles are similar to each other, then we can use that understanding to show that even their corresponding angles are equal to each other. We are going to use that approach because in these two triangles that look similar, we have all the sides. So if we can just show that these corresponding sides are in proportion, then we would have proven that the two triangles are similar to each other. Let's look at this. In these two triangles, the triangle TFE, look at the smaller triangle TFE, and triangle TCD. If we try to express their sides as ratios, let's see what we get. If we say TF over TC, that gives us 5 over 10, which simplifies to 1 over 2. If we take TE over TD, that will give us 7 over 14, which simplifies to 1 over 2. If we take FE over CD, that will be 9 over 18, which simplifies to a half. Look at these sides here. TF, 5, TC, 10. So we are looking at these two triangles here, this triangle and that triangle. So this side goes with that. And then we come to TE. We have TE, the smaller triangle, goes with TD. And then we have the side FE. FE, the smaller triangle, goes with the side CD, the bigger triangle. The ratios of the corresponding sides of the two triangles are all the same. They give us 1 over 2. Then we can conclude that the two triangles are similar to each other. Remember the reason that we use for for this condition of similarity, side, 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 because the corresponding sides of these two triangles are in the same proportion. Now that we were able to prove that the two triangles are similar to each other, we can claim that their corresponding angles are also equal. This one will be equals to that angle, and then that angle will be equals to that angle, and that angle will be equals to that angle. We can simply look at the actual triangles here. That angle F equals to angle C. Angle F, angle C. So F is EFT. Angle EFT equals to angle ECD. So this is what they wanted us to prove. EFD equals to ECD. Those two angles are equal. This angle equals to that. So we were able to find what they wanted us to find, to show that EFD, angle EFD equals to angle ECD. In the second problem, we have shown that this angle equals to that by using this condition of similarity. Remember theorem 4 of the grade 11 theorems, the angle in the same segment. If you look at this butterfly shape here, we were able to show that this angle equals to that angle. That makes point CDEF concyclic, because we've shown that these two angles are equal. From the converse of the angles in the same segment, we can say that CDEF is a cyclic quad because the angles in the same segment are equal. And then if the angles in the same segment are equal, we can claim that this one equals to that, which is what they're looking for here. We can claim that DFC, this angle here, equals to DEC. So we can claim that this angle equals to that, since this equals to that, and then that will also be equals to that. So we can claim a lot of angles. There will be angles in the same segment. Let's move now to problem 3. Here we are given that ABCD is a cyclic quad. We are given that chord DC and chord CB are equal in length. And we are required to show that MC is a tangent to the circle at C. Now, to show that MC is a tangent to this circle, we need to show that the angle made by this line and this chord DC, the angle C2, equals to the angle subtended by this chord at the circumference. So in other words, we are required to show that C2 equals to A1. If we can show that C2 equals to A1, we would have shown that MC is a tangent to the circle at C. Let's start with the A2 that we have here. So here we have enough information in this triangle ABC. We have 90 degrees, we have X. So to find A2, that would simply be 90 degrees minus X. Those are sum of angles of a triangle. So we have A2 is 90 degrees minus X. But A2 will be equals to A1. These are angles subtended by equal chords. Look, we are given that DC, chord DC and chord CB are equal in size, so they will subtend equal angles at the circumference. A2 will be equals to A1. These are angles subtended by equal chords. Now we have shown that A2 is 90 degrees minus X. So our next job now is to show that also C2 is 90 degrees minus X. If we can show that, then we would have shown that the angle subtended by the tangent and the chord at the point of contact equals to the angle subtended by the chord in the alternate segment, which is what the tan chord theorem says. Let's come to this triangle. D2 will be equals to X if you look at this cyclic quad here. This is an exterior angle of a cyclic quad. So I have this cyclic quad with this line extending to M. Therefore, D2 will be equals to B. That is an exterior angle of a cyclic quad. I have X over here. I have 90 degrees. Therefore, C2 will be 90 degrees minus X. Those are the sum of angles of a triangle. I have 90, I have X. So to find this, that will simply be 90 degrees minus X as the sum of angles of a triangle. So I found C2 to be 90 degrees minus X. I found A1 to be 90 degrees minus X. Therefore, the two angles that I was interested in are equal in size. C2 equals to A1. They are both equals to 90 degrees minus X. Therefore, I can claim that MC is a tangent to the circle at C from the converse tan chord theorem. The second question wants us to prove that triangle ACB and triangle CMD are similar. Remember, there are two ways to show that two triangles are similar to each other. We can show that the corresponding sides are in the same proportion, or we can show that the corresponding angles are equal in size. We do not have the sides here, so we would have to use the corresponding angles. Let's start with A2 in triangle ACB. A2 is 90 degrees minus X. We've proven it to be 90 degrees minus X over is the sum of angles of a triangle. And then in this triangle, C2 is 90 degrees minus X. Look at what we're doing. In this triangle, we are looking for A. In this smaller triangle, we're looking for C. So A2 is 90 degrees minus X. C2 is 90 degrees minus X. This information has already been proven. So we can just show that A2 equals to C2 at 90 degrees minus X. All this information has been proven already. ACB equals to CMD. They are both equals to 90 degrees. They are given to us. And angle ABC, which is X, it equals to D2. We've just shown that D2 is X. This is X. So the two angles are equal. D2 is X, and then ABC is also X. That has already been proven up here. So the corresponding angles of these two triangles, triangle ACB and triangle CMB, are equal in size. Therefore, we can claim that the two triangles are similar to each other because they are equiangular. Angle, angle, angle. The third question wants us to prove that CM squared over DC squared equals to AM over AB. So it would be wise always to start with what we have proven previously. See if we can find some sides in what we have already proven, the two triangles that we've proven to be similar. If you check in this triangle, we do have the side AB. We also have the side DC. So the two sides are there. So we can start with these two triangles because they are similar to each other. We can start with the side AB that we have over DC, and then would have the side BC over MD. So we took AB over DC, we take BC over MD. So the two triangles, from these two triangles, we're able to get these two sides. Now also remember that DC and M and BC are equal in size. BC, DC, they've been given to us here as being equal in size. So if we write DC, we cross multiply these two and these two, we can write this actually as DC squared because BC and DC are equal in size. So we can simply write as DC squared equals to AB times MD. This is how far we can go with the two triangles that we have proven to be similar, these two triangles here. This is how far they can take us. But to move further, if you look at what the problem wants us to show, the side AM is involved. The side AM is involved. AM, which belongs in triangle AMC. AM belongs in triangle AMC. So the triangle AMC is involved. Let's try these two triangles, triangle AMC and triangle CMD. In triangle AMC and triangle CMD, we see that they both share the angle 90. Angle A equals to angle C. We have shown it here, that C2 equals to A1. C2 equals to A1. We've shown it here. A1 is 90 degrees minus X. C2 is 90 degrees minus X. So we can start there. So that A1 equals to C2 is 90 degrees minus X. This we have already proven. Now let's look at M and M. So M is common, equals to 90 degrees. M appears in AMC and also in CMD. So M is common, it's 90 degrees. And finally, the third angle, C and D. AMC, CMD. We know that ACM, the angle ACM equals to the angle D2 equals to X from the tan chord theorem. Look, if this is our chord and we have proven this to be a tangent, therefore the whole of this angle, C1 plus C2, the whole of that angle will be equals to X. So the whole of this angle here will be equals to X, which is ACM. It will be X, an angle made by the tangent, and this chord AC will be equals to the angle subtended by the chord in the alternate segment, X. So the whole of this will be X. ACM will be equals to D2. They are both equals to X from the tan chord theorem. We have shown that the two triangles are similar to each other. They are equiangular triangles. So we can write the ratios of this triangle. We can have AM over MC and then MC over MD. Because the two triangles are similar to each other, they are equiangular. We have the side CM or MC. It doesn't matter the order. We have CM squared and MC squared. So whatever we are trying to do here, we want to have the MC squared. We already have DC squared. It's given by this. So whatever we're trying to do now is to find the MC squared. If we cross multiply that, we're going to have MC squared given by AM times MD. So if we write these two as a ratio, if we divide this by this is what we get. We get MC squared over DC squared will be given by AM times MD. And then this one will be AB times MD. So MD and MD will cancel out. At the end of the day, MC squared over DC squared will simply be AM over AB, which is what we were required to prove.